They are blah, 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 indeterminate cases. You're muted, maybe you're answering, but I can't hear a thing.
I think there's 7.
Perfect. One of them is a difference. One of them is a
multiplication.
Yes. Yes. 0 times infinity. Perfect. Two of them are
Quotients.
yes, ratios. 0 over 0, infinity over infinity. And the last three, which we have not looked at all yet, there are 3 powers. 0 raised to 0, infinity raised to 0, and 1 to infinity. Doesn't make any sense, right? No, it will. 2 conditions for Newton's method, without which Newton's method will not converge. Number 1.
Intermediate value theorem.
So no, the conditions, the restrictions, if you want.
F of x is equal to 0.
So f prime of x0 cannot be 0. So when we choose the initial value, we have to make sure that f prime is not 0. Otherwise, we cannot choose that x0. We have to start somewhere else. Awesome. What is the second restriction or condition? If this is R, and I start here with x sub 0, what should not be between R and x sub 0? What I should...
local max.
Yes. Make sure no local max or min. So make sure that's rare, but it's an important condition, right? So you have the open interval, or the closed interval, doesn't matter, right? So it's closed. So you start either here or here, the 1 unit interval. Just make sure that this, which is the x0, is close enough so there is no max min. You will know if there is a max min because you're going to go around in circles and the method will not converge. It will start with, let's say, x0 equals 1, and then you get x1 equals 10, and x2 equals -3, and it's all over the place. So then you know something is terribly wrong. If you see that the solutions do not get closer and closer to what you expect. So here, see, we started with 1, it jumped to 0.5, then it went back up to 0.64, and then to 0.65, but then it settled, right? And it continued to get closer and closer till the 5th iteration, which was the same. But if you get all numbers all over the place, then you know something is terribly wrong. Maybe you didn't enter the function correctly in the graphing calculator. Maybe it's a trigonometric function and your calculator is not in radian mode. Okay, so be careful. So here we had between 1 and 2. We started with 1. It jumped almost to 3. It's okay. If it jumps once or twice, it's okay. But if it goes on forever, no, it's not okay. Something is terribly wrong. So you see, we were expecting a solution between 1 and 2. We started with 1, but it jumped almost to 3. But then it went back to 2, back to 1.93, and then it continued to get closer and closer to something. Okay? So don't get scared. Just say, oops, maybe I didn't enter the function correctly. Maybe my calculator is not in the correct mode, whatever. Okay. Which indeterminate cases from these 7 are so-called ready for L'Hopital's rule? The others may be changed into those, but which ones are definitely ready?
The ratios.
Yes, the ratios, 0 over 0 and infinity over infinity. Only these two are ready. Don't need any manipulations, any changes, any logs, nothing. These are already included in L'Hopital's rule. This one, last time we changed it into infinity over infinity. And you will see that the other ones, if we end up having to apply L'Hopital's rule, we have to do a lot of work, but they have to change into this or this. Otherwise, we can't apply L'Hopital's rule. So we always hope that eventually these three powers, like the product, well, the difference is a little bit different. Like the product, we expect them to turn into these after some work. Okay, so before you ask your questions, I want to show the derivative of this. But before we do this, remember our first step is to analyze the function and identify how many functions it has. It's always easier to identify the number of functions going from inner to outer as if I'm evaluating for x equals 10. If I'm evaluating for x equals 10, I have to evaluate this first. So this will be number 1. Then I have to evaluate the function e to something, which is basically e to x. So this will be number 2. Then I have to I need to differentiate, or I need to evaluate, in this case, g. So this will be 3. And then at the end is 4. Now when I differentiate, it will be the reverse. 1, 2, 3, 4. So let's do this together. So h prime of x, f prime of the whole thing, times g prime of the rest, times e to a function. E to a function prime is e to the function times the function prime. Some of you wrote it like this. If you do this again, I can't give credit. This is incorrect. What is missing here to make it correct?
Parentheses?
Of course. If you don't use parentheses, please look back at your notes. I returned all your notes, all your solutions. So if you don't put parentheses, it means that this plus 1. In the chain rule, there is no plus. It's all multiplication. Some of you did change it into some plus and plus and plus and plus. No. One more time. 1, 2, 3, 4. First function prime times the second function prime times the third function prime. E to a function prime is e to the function times the function prime with parentheses. Okay, awesome. Enough of that. Any questions for me?
Yes, I have a question.
Yep.
So for the extra credit moving forward, do you ever give out partial points for it, or is it all or nothing?
You always get partial credit for everything.
Okay.
Everyone gets partial credit for everything that is good. Other
And then I had
questions?
another question.
Yes.
If you can, I was wondering if in section 4.3 in the book, I was looking at the graphs. I was just wondering if you could walk through it one more time, maybe 41.
Yes. Yes. 41, is it just a graph from the beginning to the end?
No, this is the like I guess the limitations. So it's like the f of prime of x is greater than 0 if x is not equal to 2. It's similar to
40,
39.
41. Oh, I see. Okay, let's do that. Let's start with that. Let me copy it.
Thank you.
Of course. So we have f prime of x is greater than 0 for x not equal to 2. We have f double prime is greater than 0 if x is less. Is this the one? Am I copying the correct one?
Yes.
Okay, perfect. Thank you. So f has an IP at 2, 5. And then we also have the limit as x approaches infinity from f of x is 8. And the limit of f of x as x approaches negative infinity is 0. It's a very good practice for the test and for the table especially. Good. Okay, so again, this means nothing to me. I'm never going to look at this and come up with anything. I don't want to waste my time. I have to organize all the information in the table. So I can start with these. These are the easiest. As x approaches infinity, of course, negative infinity, infinity. As x approaches infinity, f of x is 8. So this definitely is horizontal asymptote. Limit of f of x as x approaches negative infinity is 0. Okay, which means y equals 0, horizontal asymptote. Notice that this function has two horizontal asymptotes. One, they're different. One at positive infinity and a different one at negative infinity. You don't have to cross out anything. I just want to make a point. Okay, so 2, 5. 2, 5 is an inflection point. I put it in, done. To the left-hand side of 2, the second derivative is positive, which means the function opens up. Well, I would put 0 here, or you can put undefined, but I'll put 0. So this is done. The second derivative is negative for x greater than 2. So this is negative, which means this. So this is done. And then the first derivative is positive always, except at 2. Okay, fine.
Pause. Could you go back? Oh, never. Okay, never mind. I think I got it. I just wanted to verify why you put a 0 under the 5.
Here for the second derivative. You can
Yeah.
also put undefined if that's what you want, but it doesn't matter. This is an inflection point. Okay. So in order to graph this, I will start always with the asymptotes. And the function has two asymptotes. 2, 4, 6, 8. And y equals 0. 2, 5. So 2, 2, 4, 5. 2, 5 is an inflection point. So the function comes from 0, opening up, going to the inflection point, and then it changes concavity, opening down. And that's it. And it's always increasing from 0 to 5, from 5 to 8, opening up, going to the inflection point, and then changing concavity, increasing to 8. And this is an example of such a function. Good. Any questions on this?
Yes. Could you re-explain, like, when you drew the graph? Because I follow up with the table. I just got.
So it's coming from 0, increasing to
Okay.
5, opening up. From 0, increasing to 5, opening up. From 5, increasing to 8, opening down.
Okay.
Very good. Next questions, please. Anything else? The floor is open. Anything else?
Yes. It's chapter 4.5 in the book, question 11. I'm just gonna pull it up again.
You said you wanted to share your screen, or you want me to copy it?
No, to copy it.
Okay, so y
It's-
equals x minus x squared. I
Yeah.
have the book right here. I have the book right here. Okay, x minus x squared over 2 minus 3x plus x squared. What I wanted to recommend is, since we started with this, it's fine, we'll finish it. But I would like to finish whatever we need from chapter 4 tonight. And then we're going to do more work on this on Tuesday and Monday and Tuesday. So, but let's finish this one. But if you have questions like this one, hold off to them till Monday or Tuesday for the review, because I like to finish the material. Is that okay with everyone?